Yeah, started recording. Okay. All right. So I think, can it be seen now, screen?
Yes, yes.
Okay, fine. So let me see the Sunday where we closed. So we talked of what is density from the wave function. The density is always a three-dimensional quantity. We also told what is a functional. So functional of density is basically density is the input and the result is a number energy. In this case, it's energy. So that's the idea of the DFT. So you direct evaluation of density without calculation of psi. That is what DFT will attempt. And then we discussed a simple Hartree-Fock type of problem with 2 electrons are in 1s or beryllium with 4 electrons doubly occupied. And then we said there is a simplification that occurs for n electron in n spin orbitals where density can be written simply as sum of the orbitals, orbital densities. So that was very important, just to learn how to write density. So then we said, why is this important? Because DFT CPU scales as low as Hartree-Fock, but it is accurate. Then we stated 2 theorems, which are the cornerstones of the modern DFT, that for any interacting n-electron system, the exact ground state energy is expressed as a unique functional of electron density. So we'll try to come back to this today as a kind of proof that we will do. So I think this is a very important proof which we thought we'll do today. All right, so this was an existence theorem, however, because Weinberg and Kohn did not specify the exact nature of the functional. So in some way, we can say there exists a functional which expresses the ground state energy exactly, although we do not know the functional yet. So till today, the exact form is not known. So DFT eventually depends on approximate forms of the functional, and the approximations, however, are getting better and better. Hence, DFT gives a reliable result. The problem is they are not systematically improvable, though a lot of progress has taken place in this direction, and we can probably use DFT certain functionals with a degree of confidence. The other problem of DFT is that it is a ground state theory. Then we also came to the Weinberg-Kohn theorem 2, where we said, how do you calculate electron density? All right. So I think that this is basically the Weinberg-Kohn theorem 2, where we said, if you do a first order variation of that functional with respect to density, subject to this condition, that is very, very important. We have been saying, with all of the density, if you sum up, it must be the total number of electrons, and that will give you the density. Since DFT functionals cannot be exactly derived, there are many functionals which use parameters. Hence, I also want to mention that the DFT functionals are not improvable, not ab initio. Plus, they are not systematically improvable. The functionals are not known, and obviously, that's the difficult part, that they are not systematically improvable. However, a simplicity occurs in the sense that this can be. I think, can you just mute? Yeah. So the simplicity occurs because computationally it is very simple. Hence, it is amenable for large systems. So that is one of the reasons people use DFT. All right. So I think with this, I can now go to the today's talk and come back to the Weinberg-Kohn theorem. So let me, before I do that, let me do a little bit of an exercise, which is not very difficult maths, but very little exercise. So let's assume that I have a system of n electrons, which is under an external potential. So I will try to explain what is an external potential. Let me first write it. And I call this external potential some V or V1. So it means there are n electrons which are smeared. Of course, you know, electrons are like waves or particles. They're particles, but their actually density is near all over. So what will the electrons will have? These n electrons have momentum because they have density, but they are also particles, so they have momentum. And because of that, they have got a kinetic energy. Plus, they're positively charged electrons, so they have a potential, which is a repulsive potential, which is basically a pair potential between the two electrons. And in addition, there can be whatever else, I call it external potential. So it's a system of only n electrons. So of course, you have a kinetic energy, you have a repulsive potential between the electrons, and then something that is external potential. So I hope now we can relate to a molecule. So if it is a molecule, let's say methane, I call it n electrons, n is 10, right? Methane, you have 10 number of electrons. So you have a kinetic energy for 10 electrons. You have a repulsive potential for between the 10 electrons. But then there is an additional external potential which comes due to the nuclei. So I have 5 nuclei in methane, 1 carbon and 4 hydrogen in some position. And I already told you that whatever we are doing, we will do under the Born Oppenheimer approximation. So the nuclei are fixed in their place. So those nuclei and the electrons will have an attractive potential. That is external potential for the molecules. In addition, I can give an electric field, magnetic field, whatever. So external potential is a very general term, which can be just written as a V1. So there is a little part that I will do. So one is that for such a system, I have what I call the Hamiltonian. Many of you have known Hamiltonian. So it has a kinetic energy term, which is basically in some atomic units I'm writing. So I will not write too much. I will write half of Laplacian. It means that the H cross I'm not writing, the Planck's constant, etc. is 1, mass of the electron is 1. So I just write minus half of Laplacian, plus the Laplacian is basically the second derivative operator with respect to x, y, z. That is kinetic energy. So all of you know kinetic energy is momentum squared by 2m. Momentum is the first derivative with respect to position. Kinetic energy, hence, is second derivative. That's all you need to know. And there is a nice way to write this Laplacian. For those who do not know what is a Laplacian, the Laplacian is second derivative with respect to x, y, and z. So it's an operator. So this is all the Hamiltonian operator that I'm writing. In addition, it has an electron-electron repulsion, which is again normally I will write as 1 by modulus Ri minus Rj. And now this Hamiltonian is acted on external potential. So I will just write Ext. So this Ext I can write as a sum of, so that is my V1, as a sum of one particle potential for each electrons and sum over I equal to 1 to n, which means I add this 1 electron potential for each n electrons and add. So for molecules, what will be this V of Ri? So let's say I have a nucleus here, I have another nucleus here. Take a simple system of 2 diatomic molecules, and I have electrons. So each of the electron is attracted by these 2 nucleus, right? This is my nucleus 1 and nucleus 2. And this is, let's say, electron 1. Of course, electron 1 does not have a position, but it is just given R, but it actually doesn't stay at R, as you know. So for just calculating the potential, I can write that whatever is the value of R here, take the difference of this with the nucleus distance and make it an inverse. So it's again a Coulomb's law, inverse of the distance. So that will be a energy, potential, external potential. So I'm writing energy, not the force. Force has square dependent, 1 by R square dependent, and the energy is simply 1 by R dependent. So I can write for each electron such forces. Attraction due to the 2 nuclei. Then the second electron will again have an attraction to the 2 nuclei. Because nuclei are fixed, this potential is very simply written in terms of R1, R2, R3, and so on. And these are some nuclear positions which are known. So that is the reason I'm writing all the external potential is sum of V of R1 plus V of R2, V of R3. Whereas V of R1 contains electron nuclear attraction. So if I write like this, then my Hamiltonian becomes minus half Laplacian for each electron. So I sum over I plus electron-electron repulsion, which I can simply write VEE plus external potential V external of Ri, or simply VRI. Now it's a very important philosophy that is actually there everywhere, but in the context of density functional theory, we realize. Let's assume that I have a 10 electron system. Example will be very nice. Methane and another 10 electron system, let's say water. Both of them have 10 electrons, right? Now you try to imagine how, I mean, for those who have done little bit of quantum mechanics, they'll be able to think, how would the Hamiltonian between two systems differ? I'm writing both under Born-Oppenheimer approximation. So how would the Hamiltonian of methane and water differ? Because both of them have 10 electrons. If you look at this operator, Laplacian operator is exactly same. Number is also n. So this operator, this part, is identical for methane and water. If you look at the electron-electron repulsion, it is also simply 1 by Ri minus Rj, which is electron coordinates. They have 10 electrons, so 10 pairs of interaction, which is 10 C2, right? So 10 C2 is the value of 10 C2 will be the number that is the number of pairs that will happen, right? So this is also identical. So if you have 3 electrons, you'll have 3 pairs, R1, 1, 2, 1, 3, 2, 3. So till now, my Hamiltonian is identical for methane and water because there is no reference other than the number of electrons so far. So where the difference comes in is very interestingly in this external potential. If you quickly think, what is this external potential? It is the attraction of the electron in methane with the nuclei of carbon and 4 hydrogens. In this case, interaction of the electron with the hydrogen, 2 hydrogen atoms and 1 oxygen atom. So their charges are different. Their coordinates can be different. Atomic coordinates can be different because this is a Born-Oppenheimer approximation. So everything that the molecules or the two systems tend to differ for a given number of n electrons is in external potential. So I can write two systems, and this is very important to understand, two systems with same number of electrons differ only in the external potential. External potential is potential which is external to the electrons. So as you can see, when I do kinetic energy and electron-electron repulsion, that is intrinsic to the electrons. Electrons have a kinetic energy, electrons repel each other. The external potential is something that is coming from outside, maybe due to the nuclei, electric field, magnetic field, whatever. So this is the only thing that actually make the Hamiltonian of two systems with the same number of electrons differ. I think this is a very, very important point to understand. So before we come to the Weinberg-Kohn theorem, that means essentially the two electrons difference always comes from this external potential. If I now write the energy component corresponding to the Hamiltonian, it will exactly have a component for each term. So whatever, even if you do in the wave function picture, it doesn't matter. It will have a kinetic energy component, it will have an electron-electron repulsion, and it will have an external potential. So if I define the energy as various components, you will again see that this is a part which is very, very important. to distinguish. Let's now assume that the two systems, and now we'll actually come to the Weinberg-Kohn theorem. So I think you have to understand the logic very carefully. So two systems of n electrons have same density. First of all, forget about two systems. A system which has the same density of a density rho of R. I would first like us to write what would be the energy due to the external potential. So I'm only writing the part which is electronic energy due to the external potential. And this is something that you need to write it all the time. So let me now say to the external potential, sum over V. I'm just deliberately not writing V external, I'm simply writing VRI. It's a sum of one particle potential. It has all the nuclear coordinates, its atomic charge, everything. I don't care. I'm just writing as a V. It's very simple mathematics. And the density is rho of R. So how do you write the energy? So there is a relation between the energy and the potential. For all the n electron systems, if this is the only part that you have external potential, the energy that comes, and this is something that let me write it down now, the contribution of the external potential V of R for electrons which has density rho is a sum over product of the rho of R and V of R at all points and sum. As you know, the R is a continuous function. It is not discrete. So I have told you in the very first class, whenever there is a sum over continuous thing, you should replace it by an integral. So an integral which is over the entire space. So again, it's a definite integral. So by my own definition, I can say this part is a functional of rho. I hope you now see how the functionals will come, because this is a definite integral. It is over entire volume element. Entire volume element, whatever it is. So I'm just writing over entire volume element. I'm not going to write 0 to infinity, whatever, because it depends on your coordinate systems and so on. But the point is that if I have density and external potential, which is sum over all the electrons, the total energy contribution is simply for each electron. For each electron, you take density and the external potential, multiply and sum. That's all. So this is a very useful thing to realize. This comes from the physics that if you take the derivative of energy with respect to rho, you get the external potential. That's the definition of the potential. So this comes from a very fundamental physics. And that is the reason its contribution is simply written like this. Once you are able to write this, the Weinberg-Kohn theorem proof will now become very simple. Remember what we said in the Weinberg-Kohn theorem. We said that the ground state energy is a unique functional of electron density. So let me paraphrase what it means. It means that if I have two systems, so if I have two systems with a density rho, okay, then they must correspond to the same external potential. Or I can say that if I have two systems with a differing external potential, so two systems whose external potentials are different, just like I said, methane and water molecule with different external potentials, but the two systems with the same number of electrons, of let's say n electrons, number of electrons is same, but external potential is different. So that's an example that I already gave you, methane and water molecule, right? So that is a different, like methane and water molecule. They have different external potential. Then what we are saying, the two systems with different external potential must have different density. This is the meaning of the Weinberg-Kohn theorem. It cannot have the same density. The reason is the following: if you have different external potential, that means Hamiltonian is different. If the Hamiltonian is different, energy is different. So that means if they have different energy, they must have different densities. That is the meaning of unique functional of density. If two systems with a different external potential, obviously it means their Hamiltonian is different. That means the systems will have a different energy and they must have different density. This is what we are trying to prove. So let us get the proof very clear that I have two systems like methane and water. They have different external potentials. What I'm now trying to say is that they must have different density. If they have different external potential, the energies are different. Hence, energy is also a functional of unique density, unique functional of a density. So they must have different density means there's a unique correspondence. The proof goes in the following manner. Let us assume this is not true. So this is a very standard way of proving. Then we will try to show that we will reach an absurdity if it is not true. Which means, let me take two Hamiltonians, which has for the same n number of electrons, kinetic energy T. I must tell you that many times kinetic energy, and I will continue to use it, is actually symbolized by T, capital T, plus VEE and an external potential V1, which is again sum of one particle potential. And I have two Hamiltonian H2, I have another Hamiltonian H2, and I already told you if the number of electrons are same, this part and this parts are identical, so they differ on V2. They differ in external potential. So I've taken two systems of n electrons with a different external potential. Now, I'm saying that if this is not true, that means let us assume that these two have the same density. So these systems with such Hamiltonian have same density rho. Then I will prove that that is absurd. So that means this is no longer possible. That's what I'm going to prove. But let me assume. So let's assume, this is the assumption, that I have n electron systems, number of electrons is constant, but the V1 and V2 are different, but I repeat that they have the same density. All right. If you want to prove that, let me write down the energy for this system. So let's assume that this H1 has a wave function psi1. See the interesting part. I'm using the Schrodinger equation to prove the Weinberg-Kohn theorem. After proving, I'm not going to worry about Schrodinger equation. As I told you, this is not something that DFT does, just for proof. So let's say that H1 has psi1 and H2 has psi2, eigenfunction, and E2 is the energy. These are ground state energies. So if I write psi1, H1, psi1, that becomes my energy. So I will basically write with this wave function the kinetic energy component, the potential energy component, and then the V1. Okay? So I can write the kinetic energy part, then the potential energy part, and the part which is external potential in the energy contribution. I can do the same thing for E2. So I call it E1 and E2. Now let's apply what is called the variation method. I hope all of you are familiar with this notation. This is called the Dirac notation. This is essentially means the integral that I was writing, psi1 star, H1, psi1, d tau. This integral is simply written as this quantity. Okay, so I can write similarly for this quantity, for all the integral. But let me now apply variation method. I talked about the variation method in the last class. I said if you take any arbitrary function, in fact, I had already used Dirac notation in the last class, if I remember, and take, let's say, H1, this is greater than or equal to E1 all the time. Because E1 is the true ground state. If I take any other wave function, any arbitrary wave function for this Hamiltonian, the result is always going to be greater than or equal to E1. In particular, in place of psi tilde, let me take another psi 2, which is eigenfunction of H2, which means I write psi 2, H1, psi 2. It's clear, H1, psi 2. It is clear that it is not E1, but it has to be only greater than E1. It can't be equal because psi 2 is not psi 1. Psi 2 is not the eigenfunction of H1, so it cannot give E1. So of course it will give greater than E1. Conversely, if I take H2 and take the average value with respect to psi 1, it will be greater than E2. Because the eigenfunction of eigenvalue of H2 is E2, that's the ground state energy. With any other function, it is only going to be greater. So this is another function for H1, psi 2. So I'm taking for H1 psi 2, for H2 psi 1. So for each of them, it is not its own function, other function, then I'm going to apply the variation method. Let me now write down one by one these two left-hand side. So psi 2, H1, psi 2. So if you do this, you will see that I'm going to write this as, let me just write it quickly, psi 2, H2, psi 2, plus psi 2, H1 minus H2, psi 2. I hope this is a very simple algebra that you can do. I have split H1 as H2 plus H1 minus H2. So of course, if you add these two operators, H2 will cancel, H1 will remain. I hope this is as easy a mathematics as you can get. So I've simply partitioned H1 as H2 plus H1 minus H2, and I've taken the average value with respect to these two functions, psi 2, the same function. This part I now know. What is this? This is E2, because this is exactly an eigenvalue of H2. Because I have used psi 2 here for H2. So if I use psi 2 for H2, this must be E2. So I can write this as E2 plus psi 2, H1 minus H2, psi 2. I'm writing the left-hand side for the first term. Then I must analyze what is H1 minus H2. Just see the H1 minus H2. What is H1 minus H2? For same number of electrons, kinetic energy is same. Electron-electron repulsion is same. It is only the difference of two external potential. It's only the difference of two external potential, right? So H1 minus H2 is nothing but V1 minus V2, which is nothing but sum over V1 of Ri, sum over I, minus sum over I, V2 of Ri. So I am now splitting this as two one-particle potentials, the difference of that. And the whole thing can be written as sum over I, V1 minus V2. So V1 Ri minus V2 Ri. This is my net one-particle potential, which is the difference of these two one-particle potential. What will be the energy corresponding to this? I have already told you how to write the energy for an external potential. I have already told you that for an external potential which goes like this, the energy is simply rho of R, V of R. Density of that system into V of R, one particle potential. So if I write this, what is the one particle potential here? It's a difference of V1 and minus V2. So what would be, and what is the density? Density is rho of R. I have told you, both the systems have the same density. So the density is simply 1 by rho of R. So I can then write psi2 H1 psi2 as E2 plus the density rho of R into V1 minus V2. So V1 of R minus V2 of R, d cube of R, the integral of the whole thing. So here only V1 minus V2 comes with the density. So this is my first equation. And I know from the right hand side that this must be greater than or equal to E2. Remember my variation method. Psi2 H1 psi2, sorry, psi2 H1 psi2 must be greater than E1. Sorry, this is not E2, this is E1. Okay, because I am doing for the Hamiltonian one. Next, I do the second equation where the Hamiltonian becomes H2, the wave function becomes psi2. Then I have again a variation method. This will be now greater than E2. So I am now writing psi1 H2 psi1. If you apply very similar thing, then what you will get here? I will write this as psi1 H1 psi1. Oh, did I make some mistake? I think I made some mistake. This was supposed to be H1. Nobody pointed out. So this is H2 minus H1. It's just that it's a very small mistake. So this is H2 minus H1. So this will be V2 minus V1. I think it's a very simple mistake. Just 1 and 2, because I'm writing H1 here and psi2 H1 psi2. No, what was the mistake? Oh, I think I did correctly. Yeah, sorry, I did correctly. Psi1, psi2 H2 psi2. Yeah, I did correctly. Yeah, everything is right. Sorry, to confuse you. Yeah, so anyway, so I wrote it correctly. Then I write psi1 H2 psi1. So similarly, I will write psi1 H1 psi1. So first term will be E1. And then the difference of exactly reverse. Here it was H2 plus H1 minus H2. This will become H2 minus H1. So I'm going to split H2 as H1 plus H2 minus H1, which will now become rho of R, V2 minus V1, d cube of R. Okay, so here it is V1 minus V2, it is V2 minus V1, and this is greater than E2. So I have two equations. One is E2 plus this is greater than E1. Another is E1 plus this is greater than E2. So this is the two equations that I have got. Quite clearly, if you look at this part and this part, they are negative of each other, right? Because it is V1 minus V2, this is V2 minus V1, and this will cancel each other. That will lead to an equation which says E2 plus E1 greater than, what is the right hand side? E1 plus E2. And of course, this is an absurdity. I hope you understand. I get an equation which is an absurdity. Why did I get it? Because two external potentials, I took the same density. Right? To start with, my premise was wrong, that they have same density. And that is why I have landed into an absurdity. And this is how Weinberg and Kohn proved that if they have two external potentials, they cannot have the same density. That is the meaning of the unique potential. All right, I'm sorry about this little miss, but if you want, I can redo the whole thing once more very quickly in 5 minutes, so that the H1, H2 will not have any confusion. So I have two Hamiltonian. Again, I'm writing. It has a kinetic energy, it has electron-electron repulsion, and it's a V1. I have another Hamiltonian which is the same kinetic energy, same electron-electron repulsion, but the external potential is different. Both are for n electrons. So number of electrons are identical. So these parts are identical. V1 is sum over V1 of Ri or R1, whatever, Ri, doesn't matter. What you use as dummy variable doesn't matter, n electrons. Whereas V2 similarly is sum over V2 Ri. So please note that one has a V1 potential, one has a V2 potential for each electron. The external potentials are the only thing that is distinguished. So one is, let's say, methane Hamiltonian, one is a water Hamiltonian. This is all same. Then what I'm doing is the following. I'm writing Psi2 H1 Psi2. By variation method, if I do this, first of all, this must be greater than E1. That is something that you have to understand. Because Psi2 is not an eigenfunction of H1, I have taken another function. So the result must be greater than the ground state eigenfunction of H1. So that's the variation method. Then what I did is write down Psi2 H1 Psi2. So I did here Psi2 H1 Psi2. Before I do this left hand side, I'm splitting as Psi2 H2 Psi2. This is a very interesting trick. Plus Psi2 H1 minus H2 Psi2. So this, I'm now writing the left hand side. This is of course E2 because you have H2 Hamiltonian, you have Psi2 eigenfunction. So this part is equal to E2. Then I said, what is the difference between H1 and H2? Only difference is V1 and V2, which means the difference of small v1 and small v2 over summed over all n electrons. If they have same density, then this can be written as integral rho of r v1 minus v1 of r minus v2 of r d cube of r. I have already told you how to write this energy part. If you have one electron part, you can simply multiply the density because this is classical physics. The derivative of the energy with respect to density is the potential. So I wrote v1 minus v2. But in this case, my one electron potential is not v1 or v2, but the difference of v1 and v2 because I have writing this as h2 plus h1 minus h2. So I get this is equal to this. And now by variation method, this must be greater than v1. Next, I take in the variation method psi1 h2 psi1, exactly opposite. My Hamiltonian is now h2, but the function is psi1. And if I split it exactly like this, then first I will write psi1 h1 psi1. Now that I've taken h1, this will become psi1 h2 minus h1 psi1. So now you can see that I get back the left hand side because if I sum h1 plus h2 minus h1, I get h2. And I put psi1 everywhere. Psi1 h1 psi1, just like here, psi2 h2 psi2 was e2. This is going to become e1. This has the same density, so it will become rho of r. But the one particle potential is now v2 minus v1. Remember, whenever I'm doing the difference of the two Hamiltonians, T and V are cancelling. So only this is surviving. But now it survives v2 minus v1. So this will become small v of r2 minus small v of r1 d cube of r. And this must be greater than eigenfunction of h2, which is e2. Then what I do, I add these two. So I get this as an equation, this as an equation. And clearly you can see, since they have the same density, this and this cancels. Because here it is v r1 minus r2, and here it is r2 minus r1. So it is v1 minus v2. Sorry, I should not write r2. I should write v2 minus v1. Anyway, I hope you understand what I mean. In one case, it is v1 minus v2. Another case, it is V2 minus V1. So they will cancel each other, leading to an absurdity that E2 plus E1 greater than E1 plus E2. Hence, it means they cannot have the same density. So I started with two Hamiltonians, two external potential, but same density. And I said, that is not possible because it's the same density. Remember, this one particle part exactly became same. If this had, let's say, rho 2 and this had rho 1, then there would be different densities coming here, and then it's okay. They would not have cancelled, then the inequality could have come. Remember, this is an inequality. So of course, E1 plus E2 cannot be greater than E1 plus E2, right? So this is an absurdity, and this is how Weinberg and Kohn actually proved the theorem. That they said, since the external potential, different external potential has different density. So this is what we have come. The same density I cannot have. That means the different energy has a different density. Why different energy? But as soon as external potential changes, the Hamiltonian changes, right? This part is same, but this part is different. As soon as the Hamiltonian changes, energy will be different. In one case E1, one case E2, right? So different energy will have a different density. And this means energy is a unique functional of density. Those who are interested can read Weinberg-Kohn theorem proof. It is there in any textbook. It is there in, lots of websites in Google. So those who want to see, that is what I have done today. But it is the cornerstone of the modern DFT. That is the reason I had to go through this part. And since there is a request, I really looked at myself. I said, let's do it properly. So it's really very exciting way of proving that same density. They first take two Hamiltonians differing two external potential. Then they realize if the number of electrons is same, this part is identical. Okay. So when I take H1 minus H2, they cancel, only V1 minus V2 remain, or H2 minus A1, V2 minus V1 remain. Then I apply the variation method. So I do psi 2 H1 psi 2, that must be greater than E1. But then psi 2 H1 psi 2 is psi 2 H2 psi 2 plus psi 2 H1 minus H2 psi 2. And H1 minus H2 is nothing but V1 minus V2 because the rest cancel out. And we have already said if they will multiply by density and integrate. Density is same here, rho of R, so I integrate. In this case, when I take psi 1 H2 psi 2 psi 1, I have H1 here, I have H2 minus H1 here. Again, sum will become H2. And this is V2 minus V1 with the same density. So if I add this up, they cancel. And then I have an absurdity because of variation method that E2 plus E1 is greater than E1 plus E2, which means they must correspond to the different densities. I have repeated many times this part so that the proof of the theorem becomes easy. All that you need to know is that if I have a one particle potential, sum of one particle potential, its contribution to the energy is nothing but integral density times the one particle potential, which I have actually written right in the beginning. Somewhere right in the beginning, I wrote this. So if I have any external potential, which is sum of one particle potential, its contribution to the energy is just this.
But Professor Pal, Shushmita
Yes.
here. So
Yes.
it is not telling us the nature of the functionals, right?
Never.
Oh,
Never. It does not. And I told you in the last class, that is where the agony of DFT is. Weinberg and Kohn theorem only says the energy is a unique functional density. What is that functional? You go and find out.
I see.
No, I mean, no, I don't want to be. Yeah, I don't want to be very. Yeah, I mean, but this is what it is.
Okay.
The Weinberg and Kohn theorem never says what is a function. Of course, people have tried to find out, and we will see lots of attempts. But it just said it's a unique functional of electron density. So that is the whole problem. One other realization that I gave you is the following, that when I write a Hamiltonian of two of the same number of electrons of two different systems, they only differ in the external potential. This is a very important realization, which I'll come back. The kinetic energy part and the electron-electron repulsion part are identical, which is sometimes you don't realize. If I write the Hamiltonian of the kinetic energy and the electron-electron repulsion, it only involves electrons. So if I have number of electrons are same, they'll be all identical. So how does a methane differ from ammonia or from water? Only in the external potential. And that is where they come from, the different atoms, different electron nuclear attraction. And that's a very good understanding. And in the DFT, this part is called an universal operator, and its corresponding energy will be later called an universal functional. Universal because for a given number of electrons, they are identical. Of course, number of electrons will be different, then I don't compare. But all 10 electron systems will only differ in this. This is something that you don't realize till it is said, but it is actually true that they differ only in V1 and V2. And since that is a one particle potential, its energy contribution can be written in terms of density very, very easily. Just rho times the V1 or rho times the V2. Of course, here it's a difference. So I'm taking V1 minus V2. H1 minus H2 is nothing but capital V1 minus capital V2. All right, I think I have told this several times. So it should be very clear that what the Weinberg and Kohn theorem states. There are many people who tried to look at an error in the proof because people did not expect that energy can be written only in the functional of density, unique functional. Even this statement is very loaded. You know what this statement says? I don't need to know anything. If I know the density, if I know what functional it is, I should be able to write the energy. Now you can see what is the power of the DFT. The wave function was only used to prove this. Having proved this, I'm going to abandon the wave function.
Means I don't need Schrodinger equation anymore.
I'm only going to worry about the density. And density is a much simpler quantity than psi. So that's the beauty which many people didn't expect. So they thought there must be some error in the proof. So lots of people tried to find the error in the proof. The proof is exceedingly simple. There has been a lot of interpretation to the Weinberg and Kohn theorem. In fact, even recently there are lots of papers. But those only say interpretation of the Weinberg-Kohn theorem. So people might have jumped the gun. People might have thought, over-imagined. But the theorem as it is right. And this is all that Weinberg and Kohn actually said. And there is no error in this theorem. The further is an interpretation. And in that interpretation, people said there might be an error in the interpretation. But even that is today accepted that the interpretation is right. Note that since I've used variation method, these are only used for ground state, as all of you know. That means these energies must be ground state. Hence, I can qualify that this is a ground state energy. You know, I did not speak about it, but I think at the end I can qualify that whatever you have done is only for ground state energy, because otherwise variation method does not apply. Is there any more question on this proof? Because today it's 9 o'clock. I will not start anything new. So with this, we have actually developed very formal ground for density functional theory. And I'm going to talk about what is a functional, what kind of energy components are there. Then we will come to the brass track, what the computational chemists require. Exchange, correlation, basis set, where are they coming? So far, I have not discussed that, but they will all come in the next few lectures. But I would like to hear if there are any comments or any questions from anybody. It is a little bit mathematics, but I think the mathematics is not overpowering. It is just very simple plus minus. And I think please understand that this is the one part that we have used. If I have a 1 electron potential and the density of a system is rho of r, this is what it contributes to energy. This is something that I've used, dq, dense. And this is basically classical physics. So it also means, I will tell you, if I take the derivative of energy with respect to rho of r, that is V of r. You can see why. Now, if I multiply, then E will become rho into V integrated. So this integral and this derivative are the identical equations. So this is a very important part. I must tell you that ground state, this part of the energy, not the whole energy. So this part is energy is just the external potential energy. So if I take the derivative of the contribution to the external potential energy, with respect to density, it will be the external potential itself. This is potential, not the force. This is the potential energy. This is density. This is the energy contribution to this. So of course, potential energy is not itself energy. And this is the difference between classical and quantum mechanics. Okay, I have a one particle potential, but its contribution to the energy is not just the sum. It comes because of quantum mechanics, that there is psi star psi. So that's the difference. In the classical mechanics, you have simply capital V1 and capital V2. You will tell me, what am I doing? That's my energy. So, but here, I have to calculate the average value of this with respect to the wave function. And that brings me, if it is one particle potential sum, that brings me this formula of integration with rho of r. So I think this is a part which is very important to understand in quantum mechanics. And it is not just adding all the potential energy that you get total energy, contribution to that potential energy. It comes like this. Yes.
So in this proof, we have only considered systems which have the same number of electrons.
Electrons,
right?
that's right.
So
that is absolutely right.
So for systems where the number of electrons will be different. So
Yes.
the first part, the kinetic energy and the V electron.
They'll be also different. They'll also be different.
Be different.
So, so there is no question there. Anyway, they will have a different density.
So it's like we can apply this to even those systems. Where
we can apply, but that will not lead any interesting result. Here, what we are trying to say is the following: that if two systems of same electrons have the same density, or rather have the same different external potential, they must have different densities. So with the same density, they cannot have same external potential. That is all we are trying to say. They cannot have a different energy. If you take the number of electrons are different, then everything will be different. Then density will be anyway different. They cannot even have a same rho of r.
Yeah.
So that question doesn't arise at all.
Yeah.
Who are you asking? What is your name?
So I'm Audrija.
Okay.
From
Okay.
1800.
Okay, good. Yeah, so in that case, this issue doesn't come up at all. Okay, if the density is same, it can happen only for number of electrons which are constant. And what we are saying is the density is same, the potential has to be same, which means it has to be same Hamiltonian. It has to be same system. That means one system, one density. That's very interesting. So methane density is different. Water density is different. Ammonia density is different. Just because they have same number of electrons, they cannot have different density. And this leads to.
But I think Professor Pal,
yes.
Adrija's question might be interesting when an electron system would be now under interaction. Still now things are non-interacting, right?
No.
No,
they're interacting. VE has interaction.
Oh, electron, right?
Yeah,
yes.
I have not talked about it because I never required this. I cleverly avoided it.
I got that.
VE was here. What did I do? I made H2 plus H1 minus H2. H1 minus H2 does not have VE. That cancels. VE is cancelled, and here it's E2. I don't care whatever the VE. This is E2. How clever is the proof? You are right. Because if I had VE here, it was very difficult to calculate. I don't know what is VE, how to calculate two particle potential, right? That becomes the real quantum chemistry.
Mhm.
But look at the beauty. I wrote H1 as H2 plus H1 minus H2. H2 for psi 2 gives me E2. I don't need VE. Right? And this is only one particle energy. So it is interacting part. Right? Is that okay?
Yes, Professor Pal, absolutely.
Yes. Okay. Okay. So it's only the external potentials that vary. It's an interacting electrons, of course. It's not non-interacting systems. Because the fact that H1 minus H2, I'm always looking at H1 minus H2 or H2 minus H1, not individually, finally. And they cancel. That is because these parts are identical for number of electrons, which is identical. It's a very elegant proof. I mean, I would request those who are really interested. I mean, I wanted to make this lecture operational lecture on computational chemistry, so I have to get excused from Subhajit for one lecture. Okay, I'll get back to that from Thursday, where I now talk about.
This was great, actually.
Yeah. So
I know that I'm going to be wrong, but let me again just ask this: that I'm considering this VEE for water and methane.
Yes.
Now, if we just don't assume that they're interacting in a similar way because of the fact that the connectivities are different, so why would VEE?
No, they're interacting the same way. The electrons are interacting the same way. Connectivity is in the nucleus.
Mm-hmm. Okay.
Not in the electrons.
Okay. Yes.
Not in the electrons.
Okay.
It's a Born-Oppenheimer approximation. So,
right.
That is what is coming here.
Right.
That is what is coming here.
That is the external one. Right. Sure.
I would just say that somebody should simply write the hydrogen molecule. So this is electron 1, let's say electron 2, this is 2 nucleus, which is fixed. Then you realize if I write the Hamiltonian, this is R1 and R2, let's say, some coordinate system, R1 and R2. So this is 1 by R1 minus R2. Of course, I'm taking out the 4 pi epsilon 0 and all that. And here, this interaction is actually, this is fixed. So this is the one particle interaction, this is V1. V is identical. VE is simply sum over I less than J 1 by modulus of Ri minus Rj in atomic unit. That's all. It doesn't matter. It's a distance.
Absolutely. I understand that. I have been considering the nucleus, but it's they convoluted in the two terms.
Right. The nucleus is exactly what has gone in V1 and V2.
Right.
That's the external potential to the electron, and that's a one particle potential. And that is exactly what I wrote here. Small V1 and small V2. When I subtracted, its energy component is just density times this. That is what I'm saying. The fundamental thing to know is that if I have a one particle potential and a density rho of R, the energy contribution is only integral rho of R V of R. That's the fundamental thing that I told here. So I don't care. And if I take two Hamiltonians, they subtract the difference. One is methane and is water. Another is water minus methane. Finally, when I do this addition, they cancel and I lead to this absurdity. I don't need anything to know, actually. In fact, a lot of people tried. It's very good to look at the Weinberg-Kohn theorem. But the reason I was excusing myself because I wanted to make it only computational things, but I could not resist. Because Susmita asked me to prove the Weinberg-Kohn theorem. I thought I'll prove in 10 minutes, but I thought
I'm glad that you did this. Mathematics was simple enough, and so was the physics.
I thought if I do that, I'll do a very shoddy job in 10 minutes, and only 2 or 3 or 5, 10 people will understand. So I thought I'll go slow and try to make some points which are important. So this is one of the important points that I wanted to make for an external potential, one particle external potential.
So
all right. So
internal law to quantum chemistry, you put your signature in the Dirac notation. In your email,
yes.
I have seen your signature is in Dirac notation.
That is true. Yes.
So anybody who has problem with this notation,
but the only thing that you put is star in the Dirac notation.
No, that was wrong. Yeah, that is wrong.
So this is basically psi 2 star, H1, psi 2, and all the coordinate d tau of this psi. Whatever is the coordinate here, n particle, 3n particle, whatever. So I'm using Dirac notation to simplify the quantum mechanics because it's just boring to keep on writing integral. But where I needed to make the point, I wrote integral. Please remember, I did not write this in Dirac notation. Huh? That's a part because I wanted to make a point here. Okay. So, and here there is no wave function. I cannot write in Dirac notation because Dirac notation, when I want to write, there's a wave function psi star. This part is precisely now just the density is required. The rest can be integrated out. It's very interesting. In fact, I didn't prove this, but this can be actually proved. I will not try to prove it in this class, but this particular part that if you have a sum of one particle Hamiltonian, the total energy with the wave function can be shown to be this from the definition of electron density and this, but I'm not going to do this. Okay, that's a little bit of quantum mechanics. Just take this. So that's why here I don't need psi. Here I have not used Dirac notation.
Professor Pal,
Yes.
then theorem 2, HK theorem 2,
Yeah.
that is very obvious, right?
That is obvious. That is obvious. I agree. So it is just a variation method.
Yeah, it's a variation.
Variation method,
First one is
but,
only
yeah,
important.
first one is the important thing. Only thing is that in the normal variation method, they vary with respect to psi. Here the variation is with respect to rho. Because rho is my basic parameter, energy is a function of rho. So I just vary with respect to rho. So when I write E naught as functional of rho, I simply vary energy E naught with respect to rho, subject to, however, this condition. Don't forget this condition. Huh? That is very important.
And then we can apply minimization.
Yeah,
And then
absolutely.
we
That's
can
what will
find
be.
the-
That's what will be done. I'm not going to do that mathematics. I'm going to write down the energy
Sure.
component at the end.
Yeah.
Because in the next class, I'm going to discuss the different energy components. In particularly, I'm going to come the kinetic energy part where there is a orbitals will be introduced, not the density. And this is where I told you the purity of DFT will be lost. Okay. So it will become impure DFT, but that's what will be done. And then in particular, exchange and correlation. I'm going to emphasize on that. And this is where DFT begins to differ. One DFT from another DFT. And then because I have orbitals, I'm also going to use basis set. So basis set will come here. So you will have basis set and exchange correlation function. Yes.
Let's say a 10 electron system, you said water and methane, right?
Yeah.
So the kinetic energy of the electrons in water and methane will be similar?
No, because the wave function is different. It is the operator which is the same. See, the operator of the kinetic energy and the energy is different. I told you that is the difference between classical and quantum mechanics. So let me again write the kinetic energy is simply minus half
Right?
Laplacian. That's all. In atomic orbital, where mass of electron is 1, h cross is 1. It is just this Laplacian is second derivative operator. Whereas energy coming from kinetic energy, which is kinetic energy, is psi minus half Laplacian psi. This is completely different. The psi will be different. That is what we are trying to tell. That as soon as the external potentials vary, density will be different, psi 1 and psi 2 will be different, energy will be different. So for methane, this will be methane psi. For water, it will be water psi. So as soon as external potential different, V1 not equal to V2, right? That is what methane and water is. Psi 1 is not equal to psi 2. Densities are different. Energies are different. Everything is different. It was only the kinetic energy and electron-electron repulsion operators were same.
It's the external potential that does everything actually.
Yeah, then the psi, then densities have to be different, energy will be different, everything will be different. Size will also be different, actually, if you solve the Schrodinger equation. So everything will keep changing. And this is a very good realization. Why did I do Wenbach-Kohn theorem? Because it makes you think. I tell you, this theorem made me think. I have been teaching this several times, probably for 15 years in my PhD group. And every time I thought it made me think, is there an error? Is there an error? because I was an ab initio, so I never believed DFT. So I was trying to find error. Till today, I have not found. Okay, that's all I can tell you. If I find an error, I will do some great discovery. Yeah, but I've not been able to find. So many of these questions kept coming to me, but all of them have an answer. Yeah, but I'm happy that all of you are asking questions. It's 9:15, so probably I'll stop now. Yes,
Yes, I think we should close now.
Shivaji, they can stop now. Yeah.
Okay, thank you. Yeah.
Yeah. So we would have meeting on Thursday again.
Yeah.
Thursday.
Thursday at 8 p.m.
Yeah.
Yeah, I think that time it will be more of functionals and so on. All right. Thank you very much for attendance
you.
and asking questions. And I would like more and more students to also ask questions. I know one of them asked today, but I would like more of them to ask questions. Okay.
Okay, thank you.
Okay. Thank you.
Thank you.
Welcome. I'm ending the meeting. Huh?
Yeah, Professor Paul,
Yeah.
Friday 8 o'clock you are free, so we have a meeting for TCS.
Yeah, I'm free because Tuesday and Thursday only have class. So Friday I'm free. No
So
problem.
Friday we'll do a meeting at 8 o'clock.
Yeah, no problem. Okay. Thank you. Yeah.